well concrete examples. So, algorithm, PageRank algorithm, works. So let me give you kind of a heuristic picture first. Okay, so how does it work, and then maybe I can talk precisely about it, that what algorithm is and why the algorithm the way it is actually. Okay. So the heuristic picture is this. Well, so all the websites, okay, so consider the gigantic collection of the websites. Okay. We have all these websites made for different purposes. Okay, and we know that it's in huge, quantity. So what does Google is doing? Okay. So in other words, whenever I'm searching a term, okay, Google magically knows that which of the websites are most important, are the relevant to your search actions. Okay, you will see some websites appearing first, and then some other websites, and so on and so forth. And interestingly, you might have observed, or you might have felt actually, that the really interesting websites are those websites which appear on the first page, for example, when you are making a search actually. So you can go down and you can have 1, 2, and 3 actually, so on and so forth. But as you go to the more and more pages, okay, in other words, as you go and you see the more and more searches, okay, so I have a term. So imagine, that's your Google box, so you search something at Sukkur. Okay, so as you will search in a fraction of a second actually, okay, it presents you a lot of results actually. Okay, Sukkur IBA website, maybe some other website that is relevant to the Sukkur IBA, so on and so on and so forth actually. And then you will also see here 1, 2, and 3, and 4. These are the options to go and look at the more searches. More search results. You will always observe, okay, that Google magically knows all of the important websites actually, and you can mostly find them on your first page actually. It's not necessarily, but yes, you will find that the first links are the more relevant links actually. Okay. So the question is, how the heck Google knows, okay, that which websites are the important websites, and why among all these important websites, like this website should be at the top because this is the most important website actually. Okay. So the answer, so the thing that is working at the behind is basically this algorithm we call the PageRank algorithm. This is not the algorithm that is being used now. Okay, so they are using a mysterious algorithm, who knows what. We don't know about it, it's their private property. But when the Google was invented in 1990, I guess in the 90s, yes, this was their algorithm actually. They were used, and it worked for quite a number of years actually. They keep on using it, so it's it's still an interesting algorithm. If you want to make your own search engine, maybe some small search engine, maybe you can use this algorithm actually. Okay, so how Google knows that which websites are important. So it has access to all these websites. Okay. What do you think that why someone? Okay, think from a natural perspective actually. Okay. So you want to know that you have a lot of people in this university, okay? But who is the most important person in this university? how are you going to determine that who is the most important person in this university? You are going to know it that
most visited.
You know, that person who is being, you know, visited frequently. That's one thing. Or, you know, this is a good measure, okay, someone, you know, everything is rolling around it actually, so, you know, you're meeting with that person again and again, but you can also say that, you know, many of people, on daily basis, they also meet with the security guards at the gate actually. So meeting with them, just meeting is not enough. there are a lot of other things that you have to take care of it, okay. So, but what Google, you know, assumed is that, okay, you know, out of all this gigantic collection of the websites, those websites are going to be important, which are referred by many of the websites actually. So I know that every website is a website, but it also contains hyperlinks to the other websites as well. You go to a website, so it contains a link, you click there, you reach to a new website, okay, you click, you know, you reach to another website, and so on and so forth. Are you getting the point? So, which is the website, okay, which is kind of the referred mode, okay, so, which is referred mode, okay, though security guard is, you know, visited many times, but not, you know, other people will refer you to the, you know, security guard, maybe they will refer you to, for example, you know, if you're a visitor, they will refer you to, for example, you know, some sectional head, and sectional head refer you to the, you know, vice chancellor, and so on and so forth. So maybe we can reach to the conclusion that, you know, probably vice chancellor is an important guy. We all are important, but, you know, he's an important decision maker actually. So you have to think about that. So same is the case. So you have lots of websites, okay? They contain hyperlinks, but out of all these, which is referred more? Okay, that is going to be the, you know, the important website actually. Okay. So Google in their database, okay, of all these websites, they already have evaluated these rankings actually. Okay. They already have assigned a ranking to each of the websites actually. Okay. So for example, Google itself is going to have a very high ranking actually, because, you know, no matter what you do, you quite often use Google are referred to the Google. Maybe all these big websites like YouTube and, you know, Amazon and, you know, Facebook, and all these are, you know, some of the important websites, because one way or other way you are referred to, you know, some of these few websites actually. Okay, but not necessarily. Okay, it also depends on the context actually. You're making a search in that context, which website is important. Okay, so what Google has done, it has created roughly, you know, previously created a global ranking for the all websites, where each of the website has been assigned a rank actually. Okay, rank. And you know, this is like invitation to a lot of good things and the bad things actually. Okay. So how to model this situation? How to find this rank? That's what is one of the, you know, the key problem that this algorithm is addressing. So how does it compute algorithm? How does it compute the rank? So what does the Google is assuming? It assumes that each of this website is like a state actually. Okay, is like a state in a Markov chain. So that's what is the assumption. And we people are like the random surfers actually. So we go to this website, okay, it contains hyperlinks, so we go to other websites, so we switch between, you know, what do you call these websites actually. Okay, we switch between the websites. Okay. Now, so you have this random surface, so, you know, we people are like the random surface, okay. And then basically they are interested in that, you know, okay, a random surface which is going from this website, this state to other state, you know, using hyperlinks. does it stay somewhere in long run? Okay. Does it stay somewhere in the long run? The answer is yes. The question is, how can I know it actually? So how can we practically compute it this number? So we have to treat each of the website as a state. Okay. For example, imagine if I have 5 websites, say U, V, and W, and say X and Y. Okay. When U refers to Y, when U refers to Y means that V contains a hyperlink for the U actually. Okay. And U contains a hyperlink for the V, and U refers to W, and V also refers to W, W refers to X. What do you say? X. Okay. And Y refers to X. Okay. So we have it. So how can I know that which of these 4 or 5 websites are important websites? So if we keep this principle that okay, one of the highly visited website is the important website actually. Okay. Now which of all these websites is a highly visited website? We have the 2. Like this is being visited once only. U and V, they are visited once. They contain the hyperlink. It's the W. Okay. And the X. But interestingly, W and X both have is like they have roughly the same rank actually. They have the same importance because they are being visited equal number of times. So how to decide among the W and X that which is important?
X.
Okay. So X is like a sink actually. It's like absorbing the states. Once you are X, you can't. What do you call?
B another.
Is it making sense? Okay. So for the Google, so they have all these websites and it contains hyperlinks of each other. The surfer, a random surfer, is like, so you are kind of a random surfer is kind of having a random ball. So from V to U, it may start from U, may start from the website. So each of these, from all these websites, like from all of these states, it can start the random walk from any state. Go from V to U and U to V and then V to W and then W to X. Okay. So within this X is not going to go anywhere. It's going to stay there actually, and then Y to X and so on and so forth. So you have this random surface. The question is how to compute such a say that what will happen in long run. In other words, if a random surfer is surfing on in this network actually, okay, or this collection of websites for long run, where in the long run he's going to stay actually. So what can I do? So what can we do? How can we find these? What do you call this? It's long-term behavior actually. Or long-term behavior is good to know. So I can assign with okay. I can start with all, say, states have the same rank. Okay. So how many are these? So these are 5. So everyone has. So all of the websites are important actually. Okay. All are important. Okay. Then I can make a matrix that represents this Markov chain. So in other words, you can have probabilities assigned to each of it, and so this would be kind of a transition matrix. That how this matrix is going to tell you that how the random surfer is going from one state to another state actually. Okay. So it's in this state. You multiply it with the transition matrix, you're going to get a new vector. The new vector is going to have different entries actually. Just giving you a heuristic picture, not giving you a precise picture. heuristic picture. It's going to have a different, so these numbers would change actually. Okay, these numbers would change. So what to do? So apply the power method. So you keep on repeatedly apply, what do you call this, transition matrix to outcoming, vector, and see that how, this vector is behaving in the long run. In other words, does it converge to something? So in other words, here's the thing. So you start with the, say, vector x. Okay, you multiply it with the transition matrix P, so you can have maybe x1, you're going to get x2, multiply x2 with P. So in other words, get xn plus 1 by multiplying P to the xn actually. Okay, so you apply this algorithm. And you ask a question, what would be, so does this is going to have stationary, what do you call, behavior actually. So are they going to go somewhere? Is this process of transitioning from one state to another state, or one website to another website, is going to stop somewhere or not actually? Okay? The answer is that in general we know this shouldn't happen. Such kind of a problem shouldn't have a solution actually, unless this P has some specific kind of, what do you call, properties actually. Okay? So in other words, what you are saying, does this P have an eigenvector corresponding to the eigenvalue 1 actually? That's what the question you are asking actually. That's what the question you are asking. That does this P has a eigenvector corresponding to the eigenvalue 1? The answer is it's not necessarily the case that you. So this is a kind of a homogeneous system where you solve it actually. So it's not necessarily that you get a solution of such kind of vector. Okay. In other words, it's not necessarily. I'm sorry.
वो जो हमारा सिस्टम है उसमें xn है और वहाँ पर xn plus 1 है, तो यहाँ पर तो हम नहीं कहेंगे
हम ये कह रहे हैं. So what we are saying is that's what we are expecting actually. Okay. That can you, so after repeatedly doing this process, are you going to reach to some vector which will stay, same forever actually, repeatedly, no matter how much repeatedly you apply actually. Okay. So in other words, so what would be the interpretation here? So you are transitioning from one website to another website because they contain the hyperlinks of each other. The question is, is this random buffer is going to stop somewhere in long run actually? Okay. The answer is we don't know, unless we know some interesting things about the gene actually. That's what we did in the last one actually. That when you can find the limiting behavior. So when you can find the limiting behavior actually, you can find the limiting behavior of a Markov chain or a random walk if that chain is ergodic actually. So it's ergodic. So you need ergodicity. If it becomes ergodic, in other words, it becomes irreducible, and the states are essential. Irreducibility, and what was the other thing?
periodic.
Periodicity, that means you have ergodicity. So if you have ergodicity, then the previous theorem that you did guarantees that yes, there would always be solution actually. Yes, there would always, there would always exist, for example, a ranking for this website. This bunch of websites. That's what this previous theorem is essentially telling you. Is it making sense? That's how the heuristic picture is. That's what the heuristic picture is. The question is, if this x equal to px, okay, does not necessarily have a solution, then can I modify this p In other words, can I make some changes in the network, okay, so that that guarantees that you are always going to have a solution. Okay. So what does people suggested is that you consider this what you call the Google matrix actually. Let's call it a Google matrix. Google matrix. So this Google matrix is what? It's a sum of two basically matrices. So what is the first matrix? So the first matrix is this transition matrix, okay, and multiply it with D. Now, in order to have a solution for such a system, or in order to make sure that you are going to get the convergence of of the probabilities, okay, or in order to guarantee that such a ranking should always exist, what you're going to do, you're going to add another term in it, which is 1 minus D times a matrix, for example, I. Okay, a matrix R. I'll talk about their physical interpretations as well in a minute when I'll present the algorithm in its original form or prove it that why that should work. Okay, but this part, so what is R matrix? So R matrix is a matrix that contains. This is a matrix that all of its entries. Okay, all of its entries are same actually. So it contains this 1 over n and 1 over n, where n is the number of websites or the number of states in the Markov chain that you have. Okay, so all of these are same actually. Okay. Now you can ask a question. That basically what I am doing, I am modifying my transition matrix P. Why this modification should have such kind of a form? When this modification is going to be the kind of a modification where there is no much, there is not too much impact or too much change in the, taking place in the entries of the P actually. So what should I, so ideally what should I do? In other words, here's a question. I want P to stay same or close to its original form as much as possible. That's what I want. I don't want to change too much because this is the data. Okay, this is something that is coming out of the data. Okay. So what should I do? So ideally I can put 1 here. So if you choose, and D is a number, so if you choose D to be a number that is 1, so you just take away this and you get the original matrix P. If you want that these probabilities should not change it too much, you must take this D closer to the 1 actually. Because once you take this D closer to the 1, then you are multiplying a number that is closer to the 1 to the each entry of the P. So it's not going to change too much P. And if the D is closer to 1, this number is almost 0. Okay, good. This number is almost also 0. Okay. So the cleverness here is that you are not modifying too much in P. You are just adding something into your website, okay, or into your network, or into your matrix that is going to make the chain ergodic actually, and hence is going to guarantee that you have a such kind of a vector actually. In other words, for m, for m such kind of a vector must exist actually. Okay, and this X is going to contain the ranking of the websites actually. And what we are saying is that the ranking of the websites produced by M is going to be very close to the ranking to the websites produced by the P actually, because there is not much difference between P and P. So there is a typical statistically found value that usually when, for example, Google was previously using this algorithm, this value was chosen to be 0.85 actually. This was the standard value that most of the time is chosen for this. Okay, 0.85 was one of the value. Okay. So what you are doing physically in your network actually. So what you are doing, that you have your previous network that I have drawn here, for example. So you are adding. So adding this means you are adding a new state into your given, Markov chain. Okay, that new state is basically what you say. You call it a restart state actually. Okay, so it's a restart state, and you can give it a name. What do you call 0? Okay, you can give it a name 0. It's a restart state. So what's a restart? So along with your network that you have, whatever, you are connecting the third state to it is restart. And what is the probability that you are going to transition from this restart state to any of the state in the network is equally likely. Okay. So I'm not making too much change in my vector, in my what you call chain. So I'm doing is that I'm adding some states into it so that this convergence problem or the existence of the solution problem should work out. Okay, that's what it is. Before presenting the actual algorithm, I'd like to talk one problem actually. Okay, all these algorithms have weaknesses actually. You can exploit, people exploit those weaknesses. You quite often see actually. So you open a website actually, okay, maybe you'll see a lot of ads there, you'll see a lot of new pop-ups emerging from there. So you click on one website and 10 new websites are opening actually. They are referring to the new thing. So what they are doing, so they are kind of trying to catch the fake visits actually, so that we, we become important. Okay. So all these are basically a way to improve the rank of a website or their website.
They might have their own algorithm.
Yeah. It's happening automatically, but this is what we are doing. So let me give you an example. So imagine you have this vector x, w, okay, u, and v. Okay, you have these 4 websites, and this is this is the network. Okay. So out of all these websites, I can, certainly think of finding that which website is important. So you can't be an important website actually. It refers to a lot of other websites. So this can't be an important website. Okay, imagine that you have some ranking. Okay, so it has some ranking. Okay, so it gives a number here. I'll upload and you can see the details as well. So currently the ranking of U is this 0.27 actually. I want to improve it. The question is, what should what should you do? You should, and let's assume that, okay, what should you do so that its rank is increased actually. Okay. So first of all, what we need to do, probably we need to get rid of this. So don't refer to too much of it. And pretend to be the website which is
Referred the most.
referred a lot at. So what you're gonna do? And create 2 new junk pages. Okay, fake pages. Alright. Which just, which refer to you.
For refer yourself.
For referring you, we are creating a,